while we wait for other folks to go ahead and join in, um, I'll do a little bit of an intro and then, we'll go ahead and get started. And as folks come in, they can introduce themselves in the chat and all that jazz. So if this is your first time on one of our webinars, welcome. If it's not, also welcome. I'm Lashmia. I am the product marketing manager here at For All Secure, and I host webinar Wednesdays, usually once a month. And this Wednesday, we have Alex, which I'm very excited about. And I'm actually going to let him introduce himself so he can tell you about his background and all that jazz. Go ahead, Alex.
Hey, what's up, y'all? So my name is Alex Brewer. I am a technical solutions engineer for All Secure. I've been doing this for about 2 or 3 years, and I've been in the software security area for about 8 years now.
Oh, wow. So you've seen a lot.
Mm-hmm.
That's wonderful. Cybersecurity and a lot of tech fields are ever changing. And so being in the game, anything even over 5 years is huge. So Alex is bringing a ton of technical knowledge to this webinar, and of course For All Secure. And I'm very happy to have him here today, showcasing a ton of cool stuff for you guys. So if y'all are cool with it, let's get started. And then as people come in, they can catch up with us. How about that?
Sounds good.
All right, go ahead, Alex.
All right, perfect. Well, welcome everyone. Thanks for hopping in on this. I'm super excited to talk about this topic today. I think it's pretty cool. We're going to be finding some bugs, talking about open source software in particular. So we'll be talking about open source software, why it even matters to secure open source software. We'll talk a little bit about the Mayhem Heroes project. Some of you may have heard of this, some of you may have not, and that's why we'll talk about it. And some of the things that we've done with the Mayhem Heroes project, as well as CVEs that we've found. If you don't know what a CVE is, don't worry, I'll explain it later. We'll talk a little bit about fuzz testing, which is kind of the main purpose of at least Mayhem Heroes project, and also what we do here at For All Secure, and what I love to talk about, as well as selecting targets. So you're looking at open source and you're trying to figure out what makes sense to actually fuzz. We'll do a demo with Conman, which is short for Connection Manager. It is a open source Linux Unix utility for managing Wi-Fi connections. There was a bug in it that was found in 2020, I believe, that was pretty huge, and it ended up resulting in a it was something that was used by auto manufacturers, specifically Teslas, and so this exploit allowed people to actually get into Teslas and mess around with the infotainment system. We'll look at how we can actually find the exploit using Mayhem and using fuzzing, and then I'll kind of wrap up and talk a little bit about everything drives out to points, and that's gonna be where we're at. All right, so at the end of this webinar, a couple things you should be able to do. You should be able to explain what fuzz testing is. You should be able to identify good candidates for fuzzing in your code base or other code bases. If you're traipsing around on GitHub and you want to find things that are interesting, you should be able to look at, oh, this looks like a good candidate for fuzzing. You should be able to understand and explain what a CVE is. And you should be able to reproduce a well-known vulnerability using fuzzing. Not all of them, just the one that we're going to be going over today, but you should at least have the tools in your back pocket to be able to reproduce other ones. So we'll start by talking about open source software. So what is open source? Open source is just software that has been made publicly available to developers, users, companies across the world. To get an idea of how pervasive open source software is, in 2022, GitHub, which is I believe it's the largest code repository system in the world.
It is.
I think that's true. It had over 413 million open source software contributions, and that was just in 2022. You can imagine that you extrapolate that off. That's a lot of open source contributions. 97% of software applications use open source. And it's important to note here that when I say 97% of software applications use open source, I'm not just saying 97% of closed source or like private proprietary software applications use open source. This also includes open source. You can think about it this way. Open source often includes other open source, right? So when you include a library, let's say for parsing JSON or something like that, you're probably also including 20 other libraries that library depends on. So the ecosystem is very interdependent. 90% of companies rely on open source software to keep the wheels turning and keep their products and programs running. So there's lots of open source, lots of programs depend on it, lots of applications depend on it. And in the past few years, just even, GitHub dependency scans, which dependency scans are just looking at a particular repository and seeing what libraries or other code repositories that repo depends on, found over 4 million vulnerabilities in public repositories. Now, when I say that, I'm not saying that GitHub went and tested the code manually and found 4 million vulnerabilities. What GitHub did is it looked at the dependencies, the libraries that a repository depended on, and it cross-referenced it with a collection of open source vulnerability publications. One we'll be talking about today, which is the CVEs, which is managed by MITRE. But the important thing to understand about that is the dependency scanning is vulnerabilities that we know about. It's something that's been published and it shows up in some other repository, right? So you could think about this in a few different ways. One way is to think about it as just scanning for the things that you know about. What about 0 days? And when I say 0 days, I mean, what about vulnerabilities that no one has discovered yet? How many of those are lurking around in open source? You could extrapolate it. If the dependency scans are the ones that we have found, it must be a subset of the ones that we have not found. So it has to be at least 4 million, if not more. So that's kind of a big problem. And that's part of what we're trying to solve with the Mayhem Heroes program. So I'm gonna talk a little bit about the Mayhem Heroes program. This was launched last year, around April. We basically put some money into this program to go to different universities and teach university students how to use fuzzing and fuzz testing in open source applications, open source software, and find bugs. It's been working really well. People are really hungry for cybersecurity programs that are practical. Some of the university cybersecurity programs are all about policy, which policy is great. Standards are great. It's how we inform the decisions that we make, but they're not hands-on and they don't have a lot to do with actually finding and exploiting issues. And so people seem to really resonate with this. So far, this whole project has been with one goal, and that's been to make the world's software safe. Why do we care about that? Well, because we use software. We're part of the 97% of companies that are using open source software. Of course, we want to make it safe. It's used everywhere. So we should be analyzing it before it makes it into production systems. And this program, again, teaching people how to secure open source. We have all of our integrations are public. You can go onto GitHub under the Mayhem Heroes organization, and you can see all of the repos that we've integrated. To date, I believe it's about 2,000 plus projects, almost 3,000 targets that have been fuzzed, and over 200,000 defects that have been found. And if I'm numbering correctly, that says 140 billion tests run on open source repositories. This is a year. This is started in April 2022. It's May 2023 right now. So a little over a year, and we've already seen a huge amount of interest in this, and we found a lot of different issues in open source repositories. And I wanted to talk specifically about CVEs here. So if you're not familiar, the CVE system, which stands for Common Vulnerabilities and Exposures, is a system providing information and details about publicly disclosed security vulnerabilities and software exploits. This is maintained by MITRE. MITRE is a research organization funded by the government, works with Homeland Security, Department of Defense, really just research projects to make things safer. And so this CVE system is maintained by them, publicly disclosing software vulnerabilities. And to date, Mayhem Heroes participants have actually found and published several serious critical CVEs just using fuzzing and Mayhem. And one thing I want to kind of drill home here, CVEs, which are previously unknown, eventually do become known vulnerabilities that things like dependency scans search for. So when you say something like, all right, well, dependency scans find one type of vulnerability, which is a known vulnerability, and approaches like dynamic application testing, like fuzz testing, finds unknown vulnerabilities. Every vulnerability is an unknown vulnerability until it is found, meaning that dependency scans are completely useless if we don't know what we're looking for. Now, they're great once we do know what we're looking for, because it's a lot easier to look for a dependency than it is to necessarily run static analysis or dynamic analysis on a repository. That takes a little bit of effort, whereas dependency scanning, you can kind of just look at the libraries that are there. So it is a great tool, but without actually going in and finding those 0 days and publicly disclosing them, there is no dependency scanning. There are no finding vulnerable libraries. So this is a really important distinction to make. By us going into open source and finding vulnerabilities, we are making dependency scanning more robust by publicly disclosing these security vulnerabilities. Okay, I've said it a few times. I've talked about fuzz testing. Some of you might be scratching your heads and saying, what the heck is that? Let's talk about it. What is fuzzing? Fuzzing is the process of automatically sampling and testing a program input space to elicit new program behaviors. That probably didn't really clear it up for you that much, but I think it is actually a very concise and succinct definition for what we're doing. So program input space, you have a program, it does things. The things that it does are what we call known behaviors. And this is a subset of all the behaviors that a program can actually execute. So this subset of known behaviors, these usually will write things like unit tests for them. Like, make sure that we can log in correctly. We want to make sure that we can parse this configuration file, something like that. Now, programs are obviously complex, and there's lots of interprocedural calls between methods and classes that lots of variability that are just built into applications, and that's the way that they have to work. But this variability becomes unknown behaviors. And so fuzzing is really, really about exploring the unknown space, or the unknown behaviors. The known behaviors of a program is a finite space, right? Because we know about it, we can count it, it is countably finite. However, the space of unknown behaviors is potentially or theoretically infinite. Now, it's not actually infinite because it's not infinite, but within that subset of unknown behaviors, there's another set of behaviors which we could consider bad behaviors or vulnerabilities. And so what fuzzing does is it's really trying to make that subset of known behaviors larger by incorporating more known behaviors and saying, hey, this is a behavior we didn't know about. Now we're adding it to the known behavior pile. And as we continue to subsume those unknown behaviors, we might find behaviors that are bad, or that cause a program to crash, or remote code execution, or disclosure of information, things like that. So that's really what we're trying to do with fuzz testing. Here's a very simple example. So on the right-hand side, you can see a basic example of what a program might look like. This is obviously an abstraction. This is not a real program. It basically reads an input. It has some conditional checks, and then it exits. And then there is a vulnerability if some certain conditions are met. Again, nobody writes a program that has a method called vulnerability. This is just to represent that when certain conditions are met in a program, a vulnerable behavior could occur. So when you send the input mom, M-O-M, to this program, it checks if the first char is not B. It is not, and it just takes this left-hand path here and goes to OK. If you send the input dad into the program, again, same thing, exact same path. These two inputs are actually redundant. We only need one of them. Now, when we send the input BOB, we notice that a condition is met. And this is kind of the beauty of fuzzing, is that fuzzing will notice, hey, I've unlocked a new path in the program. I've met a new condition that was previously unmet. So I'm going to start generating inputs that continue to try and explore these paths that I didn't know about. And as we go on, we start to generate more inputs that trigger more conditional paths, and eventually we will find an input that triggers all three of these paths and finds a vulnerability. So in general, we can treat securing and understanding the program input space, what I was talking about earlier about the negative space or the unknown behaviors of a program, kind of like a maze, right? There's all these different portions that we maybe know about. We might know about certain ways to get through the maze successfully, and there might be a lot of other ways that we don't know about. And so in order to efficiently explore the maze, we can kind of use fuzz testing to enumerate all of those paths and collect all of those paths and see which ones lead to good behavior, see which ones might lead to bad behavior. So what is Mayhem? I've been talking about Mayhem. Mayhem is our flagship product at For All Secure, and it's something that incorporates fuzz testing as part of a series of DevOps security application security techniques, right? So we use something called advanced fuzz testing, which is a combination of a couple of other fuzzing techniques. So we've talked about fuzzing. Obviously, when you look at something like this, one way to do this would be just to generate things at random. This is kind of like the lowest level of fuzzing that's possible, which is not bad. It's not necessarily a bad thing. It's monkeys at a typewriter, right? Eventually, one of them might come up with Shakespeare, but it might take a really long time. It may take an infinite amount of time, and you and I don't have an infinite amount of time. So there are better approaches besides just random fuzzing. The first approach that a lot of fuzzers use is called guided fuzzing. What guided fuzzing does, it's an instrumented intelligent fuzz testing technique that utilizes heuristics and seed corpora to generate inputs. What is seed corpora? Seed corpora just means like a body of inputs. You have a program, it's supposed to take a certain input or a certain, like a file input or something from standard in, something like that. And so what guided fuzzing does is says, hey, give me some of that. Give me some of the inputs that the program is known to accept, and I'm going to start mutating it and finding new inputs. So this is super fast, right? Because the fuzzer doesn't have to spend time inventing like JSON, for example. You're already giving it that. So it's very fast, but it's not necessarily unique. It might generate a bunch of inputs that all kind of explore the same paths. So on the other hand, we have symbolic execution, which is a technique that explores programs by utilizing formal analysis to generate logically distinct inputs. What that means is it treats the paths, the code paths in a program, essentially as a mathematical equation and solves for that equation. The solutions are then the inputs. So if I generate a new solution and it maps to the same formula, I know that it's not necessarily interesting to me. So I am able to very quickly come up with unique inputs. And when I combine both of those techniques, what we get is advanced fuzzing, which gives me the unique inputs that I need and the speed that I need to effectively fuzz a program. And that's kind of the approach that we use with Mayhem. A lot of what I want to talk about today is not really go deep into fuzzing as a topic, but really talk about like when I'm looking at open source software and I'm interested in using fuzzing to find vulnerabilities. How do I actually do that? How do I actually determine what's the most effective thing to use? So we have a few guidelines for evaluating targets. The very first thing that you do when you're looking at open source projects is you should check if it builds and runs. If the target doesn't build, it doesn't run, there's no documentation for it, it might not actually build out of the box. And it doesn't really make sense for you to waste time looking for harnessing entry points of a program if the application doesn't even run in the first place. There is a catch here, and this is an important balance to kind of try and strike. And that is, if a target does build, but it is challenging to build or it is challenging to get building, that means beyond the maintainers, other people probably have not, they've probably been like, oh, this didn't build in 10 minutes, I'm going to move on, which means that it probably hasn't been fuzzed, which means that there might be a lot of unexplored or untested code paths in that application. The next thing you want to look at is if how the target accepts input. In order to fuzz something, as we saw before, we have to provide some kind of input to the target and monitor the target and collect feedback, right? So the target needs to take the input, sequence of bytes, and do something meaningful with that input. But these byte sequences can come from anywhere. They can come from a file, they can come from a network connection, they can come from Unix sockets, they can come from standard in, et cetera, et cetera. It's important to also understand what code is exposed to untrusted input as well. So not just, okay, this code takes input. If the input's entirely internally generated, you could fuzz it and you might find some issue with it, but that is pretty deterministic. It's never going to change. Whereas code that handles input that comes from an outside or untrusted source, non-deterministic, we don't know what it is. It could be anything. That's really interesting to start fuzzing because that's something that we could take advantage of and potentially generate an exploit for. Well, think about not just the input, but like what type of input does it expect? So anything that accepts like densely packed binary formats, that's going to be really interesting because processing binary is hard. Processing structured text formats, that's a little bit easier. You can kind of definitively say whether or not it meets your criteria. That doesn't mean that you shouldn't fuzz things that expect structured textual formats, but those are just things to keep in mind. There are really interesting projects out there, such as the protobuf mutator that can help map randomly generated bytes from a fuzzer to a structured input. This is called structure aware fuzzing. So taking fuzzed inputs and then mapping it to a struct that is handled by the program helps you fuzz those structured textual formats a little bit more effectively. Irrelevant input validation, so like checking checksums, doing asserts, things like that. While that's important for probably day-to-day operation, it's going to hinder the effectiveness of the fuzzing, so you can comment that stuff out. You might want to look at who's actually using the target. Widely used code, if there's a bug discovered in it, it usually has a higher impact. Library bugs in particular can have a broader impact than ones found in individual applications. Individual applications are going to be used for individual purposes, whereas libraries are largely general purpose things that a lot of other projects use. So remember I was talking before, open source typically includes itself. It includes other open source. So that's stuff that you could also look at as well. Is this a widely used library? Has anyone fuzzed it before? Projects being fuzzed for the first time, probably going to have a lot of bugs. Projects that are being fuzzed might only have a subset of their functionality being tested. It is not interesting to look at a project and say, hey, there's some fuzz targets. These are easy to get running. Let's go ahead and run these fuzz targets. Somebody's already written them before. It's not going to be terribly interesting to run them again. But if there's unexplored or untested paths, unexplored regions of the code bases, there should be a lot of interesting issues in those areas. You can also analyze coverage to make sure that you're effectively fuzzing the target and see if there's any gaps in your coverage. Quality assurance measures. So are there existing test suites? So unit test suites, for example, or even buzzing test suites. Is there existing code coverage metrics that are already being run on the target? Static analysis, linters, are these run continuously? If you look at the unit tests, it's a good way to determine proper library usage in addition to the target's documentation so that you can effectively create something that will help you fuzz the target. If I see the unit test typically sets this sort of thing up first, then that helps me craft a good fuzz target test or fuzz harness because I know what the program's expecting and I can easily subvert that expectation. So today we're going to take a look at a very interesting CVE deep dive. CVEs are numbered by the year they were disclosed, and then a number identifier. So it does not roll off the tongue, CVE 2021-26675. However, a lot of people give them nicknames. This one is called T-Bone, and it's specifically because it was used to get into a Tesla infotainment system. And this was found in Conman, or Linux Connection Manager. So let's talk about Conman. It is a network connection manager, and it's found in a lot of different Linux-based systems, which include Tesla vehicles. And so this T-Bone, or remote code execution exploit, found in ComSecurious. It was presented at CanSec West in 2021. There are two vulnerabilities that enabled remote code execution in Tesla. There was one vulnerability in the DNS proxy handling part of the application, and there was another vulnerability that was found in the DHCP client. They're both very interesting. Today, we're just going to be looking at the DNS proxy vulnerability. Here's a little bit of detail about the actual vulnerability. You can see that it is described as a stack-based buffer overflow in DNS proxy, and it could be used by network adjacent attackers to execute code. That's what RCE is, at a remote code execution. You can see that it has a very high severity score, or CVSS score. And this is something that's analyzed by, people to assess how exploitable is this particular vulnerability. So you see it has a very high base score, very high exploitability factor, you could say. Why is this a big deal? Okay, well, you found a remote code exploit in a connection manager. You can get into the Wi-Fi and a Tesla vehicle. Why is this a big deal? I'm going to show you a video that kind of demonstrates this exploit being used on a Tesla from a drone. So someone's operating a drone, getting in range to the Wi-Fi network, and then triggering the exploit. So you can see there that the drone came in range, was able to get access to the Wi-Fi, exploiting the CVE, and then was able to do things like open the doors and control the lights and stuff like that, things that are probably not safe. So this is a really big deal. Tesla very quickly patched the vulnerability, but for a while out there, if you were the first person who found this, you kind of had access to all of the cars that were on the road at that point. And so this is a really big deal, and it's important for us to be looking at open source and finding these things and reporting them, so this stuff doesn't happen. All right, so we know that, so what we're going to be doing today is reproducing these vulnerabilities using fuzz testing. And so we know that one of the vulnerabilities is in the DNS handling code. So we can take a look at the DNS proxy portion of Conman and try and find where we might send fuzz data so we can reproduce this exploit. So the first thing we need to do is we need to identify where we're going to create our fuzzing harness. We know that DNS generally operates over UDP. So if we look at the DNS proxy code within Conman, we'll find a function that calls recb, and that's called UDP server event. So this UDP server event here, it's it calls a recb. We know that means that it's receiving data, potentially untrusted data from an external source. And then it takes this buffer that it receives and it sends it to forward DNS reply. Forward DNS reply seems interesting to us, so that's the function that we're going to target. All right, so there's different approaches that we can use to actually fuzzing this target. The easiest one and the most straightforward one, and if you're going to be looking at open source in general, you're going to want to be looking at fuzzing something directly. Conman takes network input by default, so it should be pretty easy to just send fuzzed input to the connection manager in general, wait a little bit, eventually an input should be crafted that makes its way to forward DNS reply and automatically explores the maze. While this is interesting, it's might take a long time, and there's not really a guarantee that we'll find the bug. It can find the bug eventually, given enough time, but let's be a little bit more targeted about this. I think it would be good to actually think about how are we going to approach this target in particular and this DNS handling functionality in particular. So the second thing we could do is we could develop a standalone harness. And I'll tell you right now, this is my recommendation. In general, this is what you want to do. You want to come up with harnesses very similar to unit tests, because you can then push those up to upstream, and the maintainers of the code can run those regularly as part of their continuous integration. For Conman specifically, it doesn't actually expose the functions that we're interested in, including for a DNS reply. And so we could spend some time creating header files and separating the code base into functions and modules and being able to include all that stuff in our test targets. We could include the C file directly. Anyone who's worked with C knows that that is not best practice to include a C file directly. It can get very messy very quickly. And so while we could spend some time creating a harness and separating things out and modularizing it, at some point we become maintainers of the code base ourselves, and this becomes a bit of a harder thing to maintain. The third approach is that we could patch the code on the fly. This is the easiest thing to do because we're basically just literally editing the code and adding a function that takes fuzzed input and it sends it to that forward DNS reply. It's very easy. It's very straightforward. The problem with it is that it is modifying the source code. In general, when you're modifying the source code, it's a very fragile change, because what if the source code gets changed upstream and it modifies something that you modified? Well, now you have a conflict and your fuzz target doesn't work at all. For this particular example, because Conman is 3 years older than it was 3 years ago, and it's already been updated, it's already been fixed, we are going to patch the code on the fly. This just is the easiest lift for us right now. We could show you what exactly we would change, and that is, it's basically prevents, if we were going to add a harness, it would prevent upstream breakage. But since upstream is already changed anyways, and both of these approaches would result in upstream breakage if anything changed, we're going to go with number 3 since that's the easiest lift. In general, I highly recommend developing your own fuzz targets and standalone harnesses, but that depends on how deep you want to get into the repository itself. So the first thing we want to do for creating a entry point for fuzzing is we want to create a libfuzzer entry point. Usually it looks like this. You might be familiar with entry points. Usually they're called main. That's the entry point into a program. For fuzzing, there is a specific entry point that is not called main. It's called LLVM fuzzer test when input if you're using the libfuzzer library. And what libfuzzer does is it looks for that as the entry point and it calls that instead of main. And you can see here that it would be very easy for us to create an entry point in our code, call forward DNS reply, and pass this buffer full of fuzz data. So we've got a input vector here. This is given to us for free, by the way. The LLVM fuzzer test one input, you can think of it as the argv for main, but the fuzzer actually automatically provides it for you. So you don't have to pass anything on the command line. The fuzzer will just generate that fuzz data. Here we're copying that data into a buffer and we're sending it to forward DNS reply. You might notice that we are passing both data and buff to forward DNS reply. I'll explain in a little bit more detail later, but basically there's some caching that happens to make sure that the data, the state on the client matches the state on the server. So you're maintaining 2 separate states there. We're actually going to be omitting the state management because it is a hindrance to fuzzing, but it's something that we need to provide in order for forward DNS reply to work without actually modifying the function. Again, think about it. If you modify the function too much, you're not fuzzing anymore. You're just creating your own functions and then sending fuzz tests to them. That's not how it's operating in the real world. So we want to make sure that our fuzz data that we're sending is actually attacking what would be operating in the real world. We don't want to fuzz something that isn't realistic. So libfuzzer provides its own main function. and we only want to include conman's main function if we're not fuzzing. So one thing that we'll do is we'll wrap conman's main function with an if-in-def fuzz. What this does is it's basically a macro. If the word fuzz is defined during our build parameters, it will completely ignore the main function. If it's not defined, it will include the main function. We can also update our make file so that the C flags actually define. You'll see here define fuzz1, and then we also include this sanitizer here. And the fsanitize fuzzer tells Clang, which is our compiler, hey, make this a fuzzing target. Don't just build it normally, but actually use that LLVM fuzzer test1 input as the entry point. And then there's a couple of things that we need to do. So we need to remove some stateful code in the DNS proxy code itself. If we leave this code in, we never actually reach the code that triggers the bad mem copy. The reason for this is because fuzzing does not typically manage state. It resets the target on every run. But with libfuzzer persistent fuzzing, some of the state gets preserved, which kind of leaves us in a weird state. Like I'm using the word state a bunch of times. It prevents us from making coherent calls to the candidate function, meaning it's not making the same types of calls that we would expect in real life. So we're going to bypass some of this state management. For example, updating the cache. The cache is not going to look the same on each iteration of fuzzing. So it's, the program will be confused and say, hey, this doesn't look quite right. Why are there two different values in my cache? This doesn't make any sense. And we're not really going to get that far in fuzzing. So an argument could be made here. It's like, hey, if we're modifying code, then we're not really fuzzing it, right? Because we're modifying it in order to, it's not how the code is actually going to work. Well, keep in mind that we're modifying it for fuzzing. But once an exploit is generated, the exploit that we find can be sent to the original code, and actually, because the exploit is, we're not modifying for a DNS reply. We're not modifying the UDP server receive event. We're just modifying some of the surrounding code so that we can fuzz fast and effectively. Same reason that we're not doing the top level approach of just sending fuzz data to conman directly. We could do that. It would take a lot of time and it wouldn't be really conducive to fuzzing. We want to make sure that we're fast and as effective as possible. And so that's why we're doing some of this stuff. Once we find that exploit, we can absolutely send it to the original server and exploit the vulnerability. So now we're going to try it out, and I'll show you what that looks like here. Here I have Conman. This is a copy of Conman from 3 years ago. Obviously, it's been updated, but you'll see here. Oh, I should probably share my terminal, huh? You guys are not seeing that. Let me know if you can see
I can
this
see
terminal.
it. It's shared now.
Okay, perfect. All right, so here is Conman. There's a bunch of stuff in here, right? So we've got some code for the client. We've got some documentation. We made this fuzz folder. This is not usually in there. A bunch of supplicants, web, things like that. This Mayhem folder, which includes some configuration for fuzzing with Mayhem. Other stuff. Source is what we're interested in. And so if we look in source, I can look at, actually, I wonder if I can just open this up. Switch. Should see my IDE. I have to use Pulsar. All right. So here's DNS proxy. Here's the code, and we're looking for forward DNS. Here it is. Here is the function that we're interested in. And we want to send code here. However, there's a few things that we need to do. First, there's some state management that happens here. And so what we're actually going to do, and I'll share this with you. This is under source. Let me close this for a second. Sorry about that. I want to go top level. Okay, that's better. All right. So I showed you the DNS proxy. So I created a patch here. that basically does a lot of the updates that we had talked about before. So some of the updates that we're doing, for example, is we are, sorry. Yeah. So one of the things that we're doing is we're changing the make file, right? And we have that if in def fuzz to make sure that we're actually looking at the correct stuff. We don't want to include our main function because then we'll get a conflict. The compiler will say, hey, you have a main function and you have a fuzzer entry point. We don't want to do both of them. We only want to do one. So we need to comment out the main function. So that's what this, there's C flags here is doing. Sorry, right here. If in def fuzz, you can see here that we're creating that if in def macro. A couple of other things that we're doing, I mentioned, again, we're commenting out some of the state management stuff. We are commenting out some of the data destroying and the list management here. Again, this is stateful stuff that's going to confuse the fuzzing process and prevent us from getting very far. So we're not going to be able to see the paths that we're exploring because there's all the state management stuff. So we're commenting some of that out. And then you'll see here, this is the most important stuff. So if def fuzz, we include this LLVM fuzzer test1 input. And you can see here that it's a very simple entry point. We take that buffer, we copy the data from the fuzzer into the buffer, and then we send it for a DNS reply. So that's basically it. And you'll see here, I have this Docker file that installs some necessary tools. It runs apply on the patch, it applies the patch, and then it just builds the project. So that's what we're going to do now. We're going to build this together. We're going to push this Docker image to Mayhem, and we're going to have Mayhem actually run fuzzing on the target. So let me switch to my terminal here. You can see my terminal, hopefully. What we're going to do is first we're going to build this Docker image. Mine happens very fast because it's all cached. Thank you, Docker. We're going to push this up to GitHub container registry so that I have my package set as public so that Mayhem can pull it, and you guys can pull it as well. So if you want to pull this image, that's the name. You can pull it. It's a publicly available image. And then the last thing we're going to do is we're going to run it with Mayhem. So if I go in here to my Mayhem folder, sorry, I can look at the contents of this Mayhem folder. What's it called? Fuzz DNS. Yeah. You'll say that it's very simple. There's not a lot to it. I say, this is the project name. This is the target I'm running. Here's the command I want you to fuzz. Hey, we're using libfuzzer. That's basically it. It's very straightforward. It's just some configuration information. And all I really need to do is I need to type mayhem run, if I could spell. I need to specify the image that I just pushed, conman, and then I need to specify the mayhem file. This is not going to work because I'm inside the mayhem folder. Let's try that again. So let's go ahead and build this, or sorry, push this mayhem file up to mayhem. Mayhem will do the rest. It will pull the image and it will start fuzzing. That was quick. You can see here that I have a link to the run. I can click on this link and it will open up. I need to switch my share here. So this brings us to Mayhem, and you can see a few things happening here. So it's going to do a few things. First, it's going to look at the target itself and see if there's any exploitability factors. These are just compile flags. And then it's going to do two things. It's going to start behavior testing and regression testing. Regression testing is, hey, we generated some test cases in previous runs. Let's run them again and see if they still create bugs. Behavior testing is, hey, let's try and find some new test cases, some new inputs, and explore the path further. You can see already that we found 2 defects. This is from regression testing because I have run this before. And we already have a test suite size of 606. That means 606 inputs. We have unique inputs that explore unique paths in the program. And you can see here that Mayhem is processing all of these test cases very quickly. We've already got to about 400 in the span of 50 seconds as I've been kind of talking along here. Now, we can sit and we can watch this run. It's set to run for 20 minutes. I don't want to sit here for 20 minutes. So like any good baking show, I already have one run in the oven. We can go over here and look at it. We'll notice a few things that on average, tests run per second are clocking in at around 32,000 tests per second. If I was going to do this by hand, if I opened up Conman and I started crafting messages, it would take me so long to generate test cases and send it to the target. That's why we like fuzzing. It's because fuzzing does that for us, and it does it in a very, very fast and efficient manner. You can also see that we found these 2 defects, and I can go over here and I can click on the issues that I found. And I can see a stack trace that shows me exactly where the problem is. You can see here that it's saying it's an incorrect calculation of buffer size. The software does not correctly calculate the size to be used when allocating a buffer, which could lead to a buffer overflow. Now, if I look at my stack trace here, I'll see my LLVM fuzzer test1 input. This is the function that I declared in my DNS proxy. And you can see that it does go to for a DNS reply, which is exactly what I told it to do. I told it to take the fuzz data and pass it to for a DNS reply. Now you'll see that this for a DNS reply calls strip domains. And then strip domains actually calls this mim move, which at this point we're in standard C library. So we're using some standard C function, and it doesn't look like it's being used correctly. It looks like it's not using the correct size to allocate this buffer. This is a problem, and this can be used to overflow the buffer. And if we overflow the buffer, we can do remote code execution. So you can see that very quickly. I'm not sure how quickly this was actually found. Let me go back to my first run. Yeah, so this was the first run I did with this one. And you can see that in about 30 seconds, it found that first exploit. This is great. This is great for us because it means that very quickly we can set up fuzzing against a target, and we can find exploits in the target that are, exploitable. Things we can then file as CVEs. Then we can push this to dependency scanning, and then people all over the world who are using this connection manager, which again, very widely used open source connection manager, they can patch it and know that what they're using is safe. So a couple of things to talk about here. What are our conclusions that we've drawn from the stuff that we've discussed today? Well, companies and organizations are using more open source than ever before. A very small fraction of it is being fuzzed. Of course, the Mayhem Heroes program is trying to change that. We have the largest number of open source projects being fuzzed to date. CVEs are common vulnerability enumerations. They provide info about publicly disclosed security vulnerabilities and software exploits. And there's been dozens of CVEs that have been discovered by fuzzing open source software via Mayhem Heroes. This particular CVE that we discussed today, the T-Bone exploit, is an example of a CVE that can be found with fuzzing. There's a lot of factors that you have to take into consideration when selecting a target to fuzz. And so we discussed a lot of different guidelines, like, what is an appropriate target to fuzz? How does it take input? And we talked about kind of thinking about those guidelines when we exploited the DNS proxy exploit in Conman. There's a lot of different ways to integrate fuzzing into a project. A balance of practicality and minimum input on upstream must be achieved. So the approach we took today was very practical, but it had a pretty big impact on upstream. If I were going to do this differently, let's say I was maintaining the most modern version of Conman, one that I knew was going to be worked on, I might do this differently. I might build a separate harness rather than patching the code on the fly. There's things you need to take into consideration. Again, if you're a developer of a project, or if you're just a pen tester and you want to get the quickest way to find an exploit. In general, we know that fuzzing is an effective and powerful technique used by pen testers and developers alike to uncover critical zero-day vulnerabilities at scale. You can find the code that we use today here under my GitHub under OSS 0 days. Here's Conman, and here's all of the patch information, all of the Mayhem stuff that I used here. So you can find this on GitHub if you want to play around with it yourself. If you're interested, and I hope you are, I hope that I convinced you that this matters. You can go to mayhem.forallsecure.com. You can sign up with your GitHub account, and you can look at existing integrations under Mayhem Heroes. I can actually show those to you right now. You can take a look at what existing integrations look like. You can use those as an example or a starting point, and you can go find your own repositories and just start fuzzing. Maybe you have an open source project that you're working on yourself, or maybe you're just a security researcher and you're interested in finding more things. You are more than welcome to go do that and start fuzzing. All of our documentation is built into the product itself, so you can go to the docs here, click on that, and you can review all of the documentation as well. I think that's it. That's all I have for today. So I'll open it. I'll actually send it back over to Lakshmiya, and if there's questions, we can answer them.
So there are some questions, and I also have some too, but we're going to go with folks in the chat first. So Aaliyah asks, how often should we check for vulnerabilities in our projects? I think you're on mute.
I'm mute. Yes, I am on mute. Thank you. That is a great question. My recommendation is all the time. Let's see if I can send an example. Let me see if this is a good example. Let's go over here. So I recommend just doing it all the time. I have a GitHub action here that runs it on a per commit basis. So let me show you this here. I have a workflow that runs Mayhem on this target. It's damn vulnerable C program, so it's not a real target. Obviously, it's just it's usually for demonstration purposes. But you can see here that it is run on any pushes or pull requests, and also manual workflow dispatches. So anytime anyone contributes to the code, this workflow actually gets triggered. This is triggered asynchronously, so it doesn't prevent you from doing anything. You might have another build workflow that just makes sure that the thing builds properly. One thing you can do here is you can actually add this as a check for pull requests. But in general, I recommend putting it as part of your CI/CD. So that way you don't have to think about how often. It should be as often as you're committing the code. There are some nuances here. If you're working in kind of a large company, large organization, you might not want to run what we call infinite fuzzing, which is like fuzzing that is run for several hours or several days at a time for every single commit. In that scenario, we recommend doing regression testing, which is only running the test cases that have been generated. If you'll see here, we have a test suite of 188, and we're running at 36,000 tests per second. So that takes a fraction of a second to run those existing test suites. That can be run on a per commit basis. And then while that's happening asynchronously, you can have a behavior run that is not kicked off by commits, and that will add new tests to the test suite. So there's a couple of different approaches there, but I really like the per commit approach.
That's solid advice for sure. My question is, like, when you do discover a CVE, especially in the Mayhem Heroes program, what is the process that you guys take to report them?
Yes, so I think I had a slide for this. Basically, let's see if I can find it here. Let's see if we can find this. There is a security tab. So a lot of projects have security reporting like guidelines. Best practice is to follow that. So I might tell you, hey, go submit a CVE, go to the GitHub security advisory or something like that and report it there. But more likely than not, any like well-known repository is going to have a security policy. So follow that first. If there's no security policy, you can open a security, or you can ask the maintainers, make a pull request and say, hey, I've found this. I think this is, all right, let me see if I can share this. You guys see this?
Yep.
This was from a hackathon we did at the Naval Academy. So we were talking about submitting CVEs. Typically, you can go over to the security tab and basically report the finding. The maintainers then open a security advisory. You'd be surprised at how quick this is. Usually the turnaround for this is a couple days.
Oh, wow.
And you can say, hey, let's fix the issue. And then GitHub can assign a CVE once the advisory is published. But I really recommend following the security guidelines there.
That sounds great. If we have no other questions, I think that we can actually wrap it up. Thank you, Alex, so much for this very helpful presentation and the live demos. Like, thank you so much. Like, we have to secure things, period, especially if we're pulling things from open source projects and doing things for the public in general. So being able to, make sure that we're covering our own bases is super important. And I thank you for showing that today.
Yeah.
All right, guys. Thank you guys so much for joining us for another webinar Wednesday, and we'll see you next month. Bye.
Thanks, everyone.